Right. So in the last lesson, we defined what continuity at a point was. Now we're going to talk about defining continuity over an interval. So meaning multiple points. So we can make broader statements about a function's continuity. All right. A couple definitions first, so feel free to pause it if you're just trying to get these down. I'm going to kind of talk about them fluidly. A function f is continuous on an interval if it's continuous at every point in that interval. If f is defined on only one side of an endpoint in an interval, we understand continuous at the endpoint to mean continuous from the left or continuous from the right. The second definition goes into a little more detail about that. So continuous from the right is when we're only looking at the limit from the right and it equals the function f of a at that point. From the left is just the opposite. We're looking at the limit from the left. And so this is just useful because if we're only talking about a function on a small interval, then by our previous definition of continuity, this function couldn't be continuous at the endpoints because the limit as x approaches that endpoint would not exist. Because as we know, for a limit to exist, it has to be the same from the right and the left-hand side. But if the function's only defined on the left-hand side, that's not possible, which is why we just make this little caveat where we define continuity from one side. So we can go, okay, well, we don't need this to be fully continuous. It's just continuous from the left. And then this endpoint is just continuous from the right. And we understand that that's different than a discontinuity, right? Because it's just not defined on the other side of that. There's no discontinuity there. It's just only continuous from one side at its endpoint. All right, so this would be a little bit cumbersome if I wanted to find or show that a function is continuous at every point in its domain. Well, any function on a closed interval can have infinitely many points that you would have to check, which we don't have time to check infinitely many points one by one. So we're going to kind of use a variable to do that. And I'll show you how to do this. And our justification has to be quite formal. So it's going to feel like a proof because it is. So it says, show that the function f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval between negative and positive 1. So as I said, that function has infinitely many points on the interval negative to positive 1. So here's all we have to do. We're going to use a variable to take the place of a specific point. I'm going to say let a be part of the interval between negative 1 and positive 1. And I specifically used open points there. This symbol just means be an element of the set that follows. So I'm saying let A be an element of the set between negative and positive 1. A can represent any number in between those. All right, the first thing I'm going to do before I deal with A is we're going to check for continuity at the endpoints, like we were talking about here. So we're going to deal with the endpoints based on the left and right hand continuity definition. So I'll start with the left endpoint, meaning I need to check right hand continuity there. So I'm going to go the limit as x approaches negative 1 from the right of this function. And all I have to do is a direct substitution. It doesn't change just because we're doing a one-sided limit. You can still do a direct substitution, and if it comes out to a number, that's your limit. So 1 minus negative 1 squared, which is 1 minus the square root of 1 minus 1, which is 1. That is equal to f of 1, since all I did was a direct substitution. Thus, I've satisfied my definition of right-hand continuity at the endpoint. For the left-hand limit, I'll go the limit as x approaches positive 1 from the left. I'll do the same thing there. That's 1 minus square root of 1 minus 1 squared, which is 1, which is also equal to f of 1. And I'm sorry, I just realized I said f of 1 up here. Hopefully you caught my mistake. On this one I meant equals f of negative 1, because that's what we were testing. But on this next one, we are approaching 1 from the left. Okay, so we've shown that at the endpoints, we have left and right-hand continuity. Now we just need to show for all the points in between, but that's what this little definition of A is. So since all the points negative 1 to 1 are on the domain of this function, what I mean is you can plug any point in there in, and you'll get a return that exists, okay? You'll get an output that exists. None of those numbers will make this undefined or imaginary. So I let A be anything between negative 1 and 1, and I've already taken care of what's going on at negative 1 and 1. So I'm going to go the limit as x approaches A for this function equals, and like I said, since A is part of the domain of this function, I can just make a direct substitution. So 1 minus the square root of 1 minus A squared, right? I'm just replacing x with A. And that happens to be what f of A is. So that equals f of A. Boom, I've just satisfied my limit definition of continuity, which is that the limit as x approaches A equals f of A for all those infinitely many points on the interval in between negative and positive 1. And so let's make our closing statement. So therefore, f is continuous on the interval closed negative 1 to 1. And remember, the brackets mean inclusive of negative 1 and 1, which is what we verified the left and right hand continuity of here. Okay? All right, that's it. So I'll put my little box to indicate my proof is over. Make sure you understand that. If you don't, make a note of it so you can ask me during class. Okay, a couple theorems here. So if you have two functions that are continuous and at A, and if C is constant, then the following functions are also continuous at A. So basically any arithmetic you do to continuous functions by combining them, so through addition, subtraction, multiplication, or division, you will get a new function that is also continuous. Any polynomial is continuous everywhere, so it's continuous on the set of all real numbers, negative to positive infinity. And any rational function is continuous wherever it's defined, meaning on its domain. So remember, rational functions, you will get vertical asymptotes. So it's going to be continuous in between any vertical asymptotes or holes or anything like that that may come up. And then we just get a listing of some types of functions that are continuous at every number in their domains: polynomial, rational, root, and trig functions. Okay, with that being said, this is just an example of finding the value of a limit. No tricks here. And in this case, you really just need to do a direct substitution because this is a rational function. As long as negative 2 is in the domain, our last list said that rational functions are continuous everywhere in their domain. How do you know if negative 2 is in its domain? If it doesn't make the denominator 0, it's in the domain. So right away I can go, well, if I plug in negative 2 here, does it make me divide by 0? No, because I end up with 5 plus 6, which is 11. So no, it is in the domain. So all we need to do is make a direct substitution into all these x's, and we should be good. So I get negative 2 to the third plus 2 times negative 2 squared minus 1 over 11. And that's what? Negative 8 plus 8 minus 1. So we end up with negative 1/11. Okay, this one, on what intervals is each function continuous? So the first one is just a straight up polynomial. You noted on that previous slide that polynomials are continuous everywhere. So right away, just identifying it as a polynomial, we know that it's continuous on the interval negative infinity to positive infinity. So b is a rational function, so it will be continuous on its domain. For rational functions, to determine their domain, you're setting the denominator equal to 0 and solving. Whatever values you solve for, you have to exclude those from the domain. Every other number is part of their domain. So in this case, I want to go x squared minus 1 equals 0, x squared equals 1, take the square root, x equals positive or negative 1. Those numbers we need to kick out of the domain, and this function will be continuous everywhere else. So I'll give you a little notation. It's continuous from negative infinity to negative 1, and then we'll union, negative 1 to 1. So these are parentheses indicating open intervals that do not include the endpoints. So I've excluded negative and positive 1 here. Union 1 to infinity. Okay, and then C, we have a kind of a combination of both a square root function that's going to be continuous on its domain, and then some rational functions. So for the square root function, we need to pay attention to the radicand, meaning what's under the radical. And we always want that to be greater than 0, so we don't get imaginary outputs from our function. So in that case, the root function restricts our domain to x has to be greater than or equal to 0. Okay, so positive numbers and 0 only. The two rational functions, again, we want to look at the denominators and see, are there any values that would make the denominator 0? So for this first one, it's pretty clear that x cannot be 1, right? Because then I'd have 1 minus 1, which is 0. The second one, if you try and set that equal to 0 and solve, you get x squared equals negative 1. You get x equals plus or minus the square root of negative 1, which is your imaginary constant, which we don't deal with in calculus. So that second one we don't have to worry about. There are no real numbers that would make that domain or that denominator 0. So I just need x to be positive and it can't be 1. So my answer for this is going to be bracket 0 to 1, parentheses, union 1 to infinity. So I made it all the positive numbers except 1 and included 0. All right, so a couple theorems. If you have a function and it's continuous at b, and the limit as x approaches a of g of x equals b, then the limit of f of g of x is equal to f of b. And also, if you have a composition of functions, the limit as x approaches a for f of g of x is f of the limit as x approaches a of g of x. So just another rule for evaluating limits, this time with composition of functions. The last theorem, if g is continuous at a and f is continuous at g of a, the composite function f of g given by f of g of x is continuous at a. So we'll see a couple examples that kind of use some of this information. So where are the following continuous? That's basically what this is saying. So sine, the outer function, our last theorem was talking about composite functions where we have, like what we have here. Our outer function in this case is sine, and sine is continuous for all real numbers. Okay, there's no breaks. You guys know what sine looks like? It's just that wave function that continues infinitely in both directions. X squared is also continuous for all real numbers. Okay? Well, when you compose two functions that are continuous for all real numbers, you're going to get a function that's continuous for all real numbers. So that's just that impact R, and it stands for the set of all real numbers from negative infinity to infinity. All right, so here we have a composite function as well. We have a root function and a rational function. And we know that rational functions are continuous on their domain. Root functions are continuous on their domain. For a root function, here's what I need to look at. What's underneath the radical? I need to be assured that it's always going to give me a positive radicand. So I'll set that equal to 0 to see if it's even possible. But in this case, you would end up with x squared equals negative 7. And again, you end up with imaginary numbers that we don't use in calculus. So no worries there. There are no values of x that would possibly make that radicand negative. But we also, in this case, don't want the denominator to be 0. So now we're going to take a broader view at the overall denominator. So we don't want x squared plus 7 minus 4 to equal 0. So now let's see if we can solve this, and we may have to eliminate some values from our domain from there. So root x squared plus 7 equals 4. I'm going to square both sides. X squared plus 7 equals 16. All right, x squared equals 9. X equals plus or minus 3. So I need to exclude those values from my domain. And everywhere else, this function should be continuous. So I'm going to say that it's continuous on the interval from negative infinity to negative 3, discluding negative 3, union. Negative 3 to 3, still discluding both of those endpoints, union 3 to infinity. Right, there we go. Okay, here's a quick example for you. Which of the following functions is not continuous on the interval between negative and positive infinity? So on the interval of all real numbers. One of these is not continuous there. See if you can come up with which one, and we'll discuss it in class.